So, in the fourth lecture, we will talk about particle detectors. Now, particle detectors are the eyes and ears of an experimental nuclear or particle physicist. Just as our five senses tell us about what is going on in and around the world, uh, particle detectors tell us about what is happening when particles and nuclei interact with one another, and what it tells us about what the products that come out, their various properties like energy, momenta, position, angle, and so on. In any nuclear or particle physics experiment, the choice of a detector is decided by the physics goals. What is it that you want to do? What is it that you want to measure? But also by what can be built, because you might ask for the moon, but you are in the real world, you will have to decide what can be built. Of course, it may not have been ever built before, but at least something that you expect to be, that it can be built. And sometimes, as I said, it could be for the first time that you are building this. Examples are the largest detectors at the LHC, the Large Hadron Collider at CERN, or the gravitational wave detector, and so on. An extremely important part of most of the detectors, there are some passive detectors as well, but most of them, is the electronics that translates the physical process into an electrical signal which comes out of the sensor that is used in the detector, which is part of the detector. And then this can be measured, it can be quantified, it can be digitized, and so on. The electronic signal is then processed, digitized for both online analysis and monitoring, but then also it is stored on devices such that you can do a very detailed scrutiny of that later. Finally, computer-based software analyzes the data and then presents it in forms that are useful to both the researcher himself and to his colleagues and to the people at large. These are some references for this talk. There is these books, textbooks, Techniques in Nuclear Particle Physics by Leo, Radiation Detection Measurement by Knoll, Introduction to Experimental Particle Physics by Furneaux. Of course, there are many books that are also coming out. These are somewhat older versions, but the first two are sort of classics in this field. Then there are also journals, handbooks, and web resources. Journals such as Nuclear Instruments and Methods, the IEEE Nuclear Science Journal, Reports on Progress in Physics, Annual Reviews in Particle and Nuclear Science. Then there are proceedings of various detector conferences. The e-resources, basically data, that is there in Particle Data Group Handbook, which comes out regularly in PhysRev D or Physics Letters. Now it also comes out in a Chinese journal. And then there are the CERN e-resources. There is also the NNDC, which I have forgotten to mention here, which is a resource in the Brookhaven National Lab. They maintain that. And there are several others. These are just a sample of the resources that we have. Okay, what are the kinds of particles that we want to detect, and what are the detectors themselves? Well, we want to detect charged particles such as the electron, positron, the mu plus, mu minus, the pi plus, pi minus, the kaons, and a host of such charged particles. Also the weak bosons, W plus, W minus, protons, we want to detect nuclei, and some of the lighter ones are given here, but you can go right up to the heaviest ones. In fact, even up to the super heavy elements that we have now produced. Then there are the neutral particles, such as the photon. Photon is chargeless. So, for example, you might want to detect X-rays, gamma rays. Then there are neutrons. Neutron is a strongly interacting particle, but it's chargeless. Of course, it has a magnetic moment, but that is not that useful in the detection process, although in some indirect way this can be used to for detection as well. But then there are neutrinos, which are weakly interacting neutral particles. Then strongly interacting particles such as the pion, the pi zero, etc. And how we detect these neutral particles is via secondary interactions such as actual reactions or their decays, where you produce charged particles. And the charged particles are detected, and then the neutral particle energy momentum identification, etc., is reconstructed. What kinds of detectors are used? There are passive detectors, such as plastic track detectors, photographic emulsions, films, mica, and so on. Uh, they are kind of frozen. Once the particle produces a track, it is frozen in time. Then later on, you have to measure properties of that track, thickness of that, the length of that, and so on. Then there are active real-time detectors, such as gas, scintillation detectors, semiconductors, Cherenkov, etc. An ideal detector, of course, has a fast time response and recovery. It has a high energy resolution. It has to be radiation hard because it might see a lot of radiation, a lot of particles. It should ideally be very cheap, and especially so, this is important for large detectors. It should be rugged, both mechanically and chemically. The detector, if it is machinable, and that can of course only happen when it is a solid detector, then it is useful in making various shapes. It should have good particle ID, and also this is useful. This can be done using tracking in the magnetic field or pulse shape discrimination, energy loss in a detector stack, etc. Alas, nothing is perfect in life, and so also in detectors. No detector is perfect. So the best properties of some detectors, and actual detectors will have some of these properties, not all of them. The more of these properties that they have, of course, it becomes a better and better detector. So in terms of time response, the time resolution for the best detectors is of the order of 10 or more picoseconds. The energy resolution is of the order of 1 in 1000. Delta E, full width at half maximum by E, is of the order of 10 to the minus 3. The momentum resolution of the order of 10 to the minus 4. This, of course, is done in detectors or spectrographs that combine magnetic fields with detectors at their back end. Then you want the best position resolution that can be got is of the order of 10 micrometers. The particle ID, that means the ability to identify or distinguish between, let's say, pi plus, pi minus, or mu plus, mu minus, and so on from each other, when there is a whole host of these articles, the best particle misidentification, I say, is about 1 part in 10 to the 6, 1 in a million. Of course, most real detectors are not that great in particle ID. Some can be even of the order of particle misidentification can be of the order of 10% and so on. Radiation hardness, again, for the best detectors is of the order of 10 to the 15 particles per square centimeter. So this can be over a period of time, and then they go bad. They start losing their properties. So this is so for minimum ionizing particles. That means the charged particles which have minimum ionization. That happens typically of the order of 1 GeV per nucleon, and less, of course, for electron and so on. The cost should be low, especially for, as I already mentioned, for large size detectors of neutrinos, or for instance, when you are looking at proton decay and so on searches. Okay, now what is there is a basic difference in the way charged particles and neutral particles propagate in matter, or the penetration of charged particles and neutral particles in matter. For instance, what is plotted here is the distance in the medium in arbitrary units and the fraction of the charged particles transmitted. So you can see that for charged particles, you have 1 at small distances, and then it drops off to 0, and the halfway distance is usually termed as the range of the particle. Of course, there are fluctuations in this range, so some particles might stop a little earlier and some might stop later, because after all, the energy loss mechanism is stochastic in nature. So sometimes you can lose a little more energy on the way, and therefore it can stop a little earlier, and sometimes you might lose less energy and then it might penetrate a little more. Okay. On the other hand, neutral particles exhibit a probability of their interaction with atoms of the medium or nuclei in the medium, and they exhibit a exponential fall off. Okay, so they are, I mean, strictly speaking, they never go to 0. This probability never goes to, this fraction never goes to 0. So there is this basic difference, that it goes down exponentially as a function of distance in the medium. Okay, so let's now look at a typical stopping power, that means the energy loss per unit length, or it is sometimes even written in terms of centimeters square per gram, because that takes care partly of the fact that you, in a gas, you might have different densities, but the thickness in terms of gram per square centimeter would be then the same, and so it would have a very similar energy loss per gram per square centimeter. So, what is plotted here on the x-axis is the momentum in terms of GeV by C. Of course, so this part is roughly in the MeV by MeV by C scale, and it is a TeV by E scale. And on the y-axis is plotted the stopping power, MeV per gram per square centimeter. So you can see that at very low momenta, there is a rise in the dE by dx. Stopping power also, you can write it down as dE by dx, energy loss per unit length. So this rises and then reaches a maximum and then falls. Okay, and then beyond a certain higher energy, it very slowly rises. The rise is logarithmic, and since the muon is about 200 times heavier than the electron, at a certain energy, you start getting radiative losses. That means you start losing energy. Not so. So in this region, the energy loss is by exciting the electrons and also by Coulomb scattering. Here it is by electronic excitation, electronic or molecular as the case may be, depending on the material it is encountering. And then there is a minimum ionization, and then it rises logarithmically because of the relativistic effects. And here there are radiative effects. It starts losing energy by emitting photons, Bremsstrahlung photons. The energy loss of electrons and positrons in lead is what is plotted here. So again, d by dx, but scaled by a certain length and by 1 by E. So as a function of energy. So you can see that the electron positron, basically the ionization part, the energy loss follows a very similar behavior. Positron is slightly more. And this is, as I said, this is for lead, which has this characteristic length is of the order of 6.37 gram per square centimeter. The contributions for the electron are through so-called Mollier scattering. The electron scatters off the electron in the medium, and since the electrons are identical, then you get two amplitudes contributing to this, namely the direct amplitude, scattering amplitude, and the exchange amplitude. In the case of the positron, you have both a direct term as well as a term which involves annihilation in the intermediate state, and then again generation of E plus E minus, so that you get E plus E minus again in the final state. So slightly different processes contribute to the energy loss of the E plus and E minus in a medium such as lead. And since lead has a high Z, it can also contribute to Bremsstrahlung, and this becomes more and more important as the ionization contribution decreases. The Bremsstrahlung contribution takes over, and so typically this happens at about 8 MeV or so, of the order of 10 MeV, you might say. Okay, if we go back to the earlier slide, the Bremsstrahlung contribution starts increasing for the muon at much higher energies of the order of about 10 or so GeV. Okay, so the stopping power of heavy charged particles in matter, as I already said, the charged particle loses energy by its interaction with the electrons in the medium. They're the lightest, they can carry away momentum, and momentum squared by 2m in the non-relativistic case. Since the m is small, they can carry away some energy for each of these. So depending on the impact parameter of this charged particle with respect to the electron, you can lose much more or less energy. Now, this is important for velocities which are about 5% or more. At lower speeds, the charged particle loses energy by scattering of the nucleus, and that becomes important. And then, of course, nuclear scattering depends on the z of the target nucleus, and so it goes like z squared. Uh, okay. Uh, the speed at which this happens, of course, shifts to higher values for heavier ions from protons to uranium, since the nuclear scattering is dominated by Coulomb scattering, which is proportional to, as I said, Zp squared. So, the proton Zp is 1 for a uranium ion hitting a medium, or that is 92. So, this is especially important for heavy ions. For instance, one example is fission fragments, which have typically Z of about 40 to 50, and with energies of 1 MeV per nucleon, per AMU or nucleon. Nucleon is used for neutron and proton. So, at these energies, the stopping is dominated by nuclear stopping. At higher energies, it is the electronic ionization that contributes to stopping of heavy charged particles in matter. Electrons and, as I said, positrons show slightly different behavior because of their low mass, and because then they can scatter of the electrons, and there are two processes that contribute for electron, and similarly two diagrams that contribute for the positron. Since the electron has a very low mass of the order of half MeV, the rest mass of the electron is half MeV. So, it becomes relativistic at energy of the order of 1 MeV, and then can lose energy through Bremsstrahlung, where you have photon emission in the Coulomb field of a nucleus. Of course, you can also have photon emission in the Coulomb field of an electron. Uh, However, there are only Z electrons, whereas the Coulomb field of a nucleus is proportional to Z squared, because all the protons in the compact nucleus contribute coherently. So, the contribution of the electrons is towards Bremsstrahlung, as compared to that due to the nucleus is of the order of 1 by Zp. These photons, of course, can lead to an electromagnetic shower, in the sense that once you produce the photon can again interact with the nucleus to produce the electron-positron pair, and then the electron-positron pair can annihilate to give you two photons, and so on. So, once you have these processes contributing, so the number that I mentioned there of x0, that is a measure of the length over which the energy of the electron or positron decreases by 1 by E. Okay. So, in lead it is of the order of 6 centimeters. So, the electromagnetic shower, of course, can be contained within a few times x0. Okay. Now, how do gamma rays in particular? Well, gamma rays are quite interesting. Electromagnetic probes are some of the cleanest probes that we have of matter, of nuclei, of particles, processes, and so on. So, gamma rays interact with matter in three different ways. One is the photoelectric effect, where a photon interacts with an atom to produce an ion, positively charged ion, and electron. The energy of the electron is related to the energy of the photon by E gamma minus the binding energy, and so the threshold, of course, for this process is the binding energy, and the probability of this process occurring, I have not yet defined the cross section, but the probability for this process is proportional to Z to the 5 and inversely proportional to the E to the 3.5. So, it is important in heavy targets and at low energies, relatively low energies. The second process is that of Compton scattering, where a photon interacts with an electron to produce scattered photon and a recoil electron. So, this could be bound or it could be free in a metal, I mean semi-free, because of course, it has a work function for even the conduction electrons in a metal. So, the photon energy is related to the scattered photon energy is related to the incident photon energy by this relationship, where theta is this scattered photon angle. The probability for such a Compton scattering process is proportional to Z of the target and inversely proportional to the energy. Of course, it occurs at all energies. Similarly, the pair production has a threshold, because after all, photon is interacting with the nucleus to produce a E plus E minus pair and a very small recoil of the nucleus itself. Of course, as I said, it can occur also on the electron. This occurs beyond the energy threshold of 2 times the mass of the electron, because you have to produce a E plus E minus pair. Also, I should point out that this cannot happen in free space. So, a freely traveling gamma ray cannot just suddenly disintegrate into two real E plus and E minus. It can do that virtually, but not in real terms. And that is because you would violate the energy momentum conservation. The probability for this process occurring is z squared, where z refers to the target z, and goes only logarithmically as E gamma by MEC squared. Okay. Here are two plots of cross sections, which basically is related to the probability of interaction with respect to the target atoms in carbon as well as in lead. So, this is a light element, this is a heavy element, and these are experimental points. So, you can see that initially it is the photoelectric effect that dominates, and there are ways of course identifying that this is the photo effect. Then there is Compton scattering, and then there is pair production. Okay. So, this takes over at relatively higher energies in the case of carbon because of the low Z of the target, and this is the way it changes for lead, where the pair production takes over at a few MeV itself. Okay. Charged particles in refractive media also emit a different kind of radiation, the so-called Cherenkov and transition radiation. The Cherenkov radiation is quite akin to a sonic boom. When let's say a supersonic aircraft travels at a height, let's say, you get this sonic boom. So, it is traveling at a speed greater than that of sound in that medium. Then you get a wave front which spreads out, and the same somewhat similar thing happens when a charged particle moves in a medium at a speed greater than that of light in the medium. So, the speed of light in the medium is defined by c by n. So, if the velocity of the charged particle is greater than c by n, then it emits Cherenkov radiation, and this is basically in the visible, near visible regions in a forward cone. That forward cone is defined by 1 by the refractive index times the beta. Beta is just the v by c. So, the velocity speed of the particle relative to the velocity of light in the medium. So, let us say beta is of the order of 1, it is a relativistic particle, then the cosine of that angle is just given by 1 by n approximately. Okay. So, if n is let us say 1.5 as in glass, then this is like 0.67 cosine theta. Okay. So, this defines basically a cone which is useful in identifying the original direction of the radiation. While the number of these photons is small compared to, and we will talk about this, the kind of detector which is a scintillator detector, it is about 200 for 1 MeV energy loss, 200 Cherenkov photons, and it is of the order of 10 to the 4 for 1 MeV loss in a scintillator. So, it is about 50 times smaller, but it has the advantage that it is information about the direction of the particle. In a scintillator detector, you excite states in the atom or molecule, and then the de-excitation takes place in all directions in 4 pi. So, you lose directional information of the original particle that created this. Somewhat analogous to this is the so-called transition radiation. This is emitted by a highly relativistic particle when crossing the boundary between two media. So, if there are two media, then again it travels from one dielectric medium to another dielectric medium, and then there is a emission of this transition radiation. Intensity is proportional to gamma, which is basically the total energy divided by the rest mass. So, this is useful in highly relativistic particles. The gamma is defined here, 1 minus beta, so beta I have already defined. But of course, this is much weaker than even the Cherenkov radiation. This is useful in very high energy physics detectors where you want to identify highly relativistic particles. Detecting neutral particles. Now, how do you detect neutral particles? As I already said, neutral particles cannot be detected as such because they do not directly produce ionization. They have to interact with matter. They do not interact electromagnetically, as neutral. However, they interact with matter, for instance, through the strong interaction or through the weak interaction. In the case of neutrons, neutral pions and so on, they interact via the strong interaction. Neutrinos, on the other hand, interact through the weak interaction. And once they produce through the interaction charged particles, then those charged particles can be detected and you can infer about the neutral particle from there. So, neutrons, for instance, can be detected via elastic scattering on protons, let's say, and protons can be part of a detector, or through radiative capture and then the photon is detected, or through NP, N alpha reaction, again the final state proton alpha are the charged particles. Neutrinos, on the other hand, can interact through the so-called charge current interaction, whereby you can produce a charged particle. In this case, for instance, when a nu E interacts with a neutron, you get a proton, or through the neutral current interaction. When neutrino interacts with the deuterium nucleus to produce inelastic neutrino, but then also a neutron and proton. And the proton as well as the neutron can get detected, and then of course the neutron has to be again through a secondary detection, but you can then infer about the neutrino this way. What are the kinds of particle detectors? Well, you have gaseous detectors, and this includes ionization, proportional, avalanche, liquid. This is just a sample of some of these detectors. You also have the TPCs, the time projection chamber. You have scintillators, and then there are broadly two types: inorganic crystals such as sodium iodide, thallium dope, barium fluoride, lead tungstate. Then there are organic compounds, both solid, anthracene, stilbene are examples of that, or they can be liquid scintillators, which are based basically on benzene, xylene, linear alkyl benzene, and so on. But they also have to have a small amount of fluor and a wavelength shifter. Then there are semiconductor detectors such as silicon, high purity germanium, and also mixed compounds such as cadmium telluride and so on. Then there are, as I already said, the Cherenkov transition radiation detectors. There are cryogenic bolometers where you actually heat up the sample a very teeny weeny amount and you measure the rise in the temperature. And these have come of vogue in recent times in the areas of neutrinoless double beta decay and so on. And of course, there are these plastic and mica detectors for tracks. There are radiochemical detectors again which are passive. So, these are examples of passive detectors, but then there are also superheated liquids. So, you can produce actually acoustic signals and you can detect events due to both neutral and charged particles. Now, of course, an extremely important part of measurements with detectors is that you have to know the detector response and you have to calibrate it. Now, this can be done either using cosmic rays, radioactive sources, or accelerator based secondary beams. So, you quantify the response, and then of course you have to do calibration from time to time because detectors response usually drifts very slowly, maybe a percent or a fraction of a percent or a few percent. So, it depends on the application. Typical detectors pictures are shown here. For instance, this is a silicon array and a bismuth germanate scintillator array, which was used in an experiment by us to measure the radiative capture in alpha plus alpha reaction. This is a plastic detector array for measuring neutron spectra using the so-called time of flight technique. So, this is a typical time of flight spectrum. So, the fastest particle, this time increases this way. So, the photon is the fastest, and then there are slower and slower neutrons, and then from this time of flight spectrum you can infer the energy spectrum of the neutron. This is an inside view of a huge water Cherenkov detector which measures neutrinos, cosmic rays, proton decays and so on. It's called the super Kamiokande detector, but it's pure water looked at by very large photomultiplier tubes, almost 50 centimeter diameter photomultiplier tube that has been used to measure atmospheric, solar and accelerator produced neutrinos. This is another example of a huge detector at the Large Hadron Collider, the so-called LHC, and this is one of the large detectors called the Compact Muon Solenoid, the CMS detector. So, the collisions take place at the center of the detector, and then there are layers. There are so-called tracking detectors made of silicon arrays which almost cover 4 pi, all surrounding the interaction zone. Then there are electromagnetic calorimeters, then there are hadron calorimeters, and then finally there are muon trackers, because the muon is the most penetrating particle. So, and then overall there is a solenoidal magnetic field of the order of few Tesla, and that helps track the charged particles that are produced, and through that both the angle and the momentum is measured. Okay, so in summary, I have talked about, I have discussed a little bit, very briefly of course, we will come to details in subsequent lectures, particles and their interaction with matter as the basis for their detection, and we have also seen some examples of real life particle detectors. Thank you.